Greetings and welcome. In this screencast, we take a look at how to construct a slope field or a direction field, which is a way for us to take a look at solutions to differential equations in a Calculus 2 course. Differential equations, just to be clear, are equations that contain a derivative of some kind. So there is a derivative in the equation. We are looking to work backwards and see the y values, see the y functions that generate those derivatives. So in this particular case, let's generate a slope field. And the slope field we're going to generate, this is -1 and -2 and 1 and 2. And maybe we'll generate like so. And what traditionally happens is that there are these dots in your slope field at all of the lattice points. They're just dots where we're going to make little pieces of tangent line as we go. It just marks where the lattice points are, the points in the plane where the coordinates are integers. So in this case, the slope of the tiny piece of tangent line every time we draw it is -2x. So when x is -2, the slope of the tangent line is always -2 times -2, that's +4. So at each of these lattice points, we would draw a little tiny piece of tangent line with slope 4. That's fairly steep. In fact, at x equals -1, then the slope is -2 times -1, that's +2. And so that's still positive, but it's less positive, right? It's less positive. It's still positive, but it's less positive. And at x equals 0, the teeny tiny pieces of tangent line all have slope 0, -2 times 0. And we could just go on and do these. These all have slope of -2, and these all have slope of -4, which are in fact very steep in a negative direction. This is a slope field or a direction field for this differential equation. Now, they give us the impression that as we sweep from left to right, the solution curves have big slopes, then less big, then 0, then negative slopes, then negative big slopes. And that shouldn't surprise anybody because we know what kinds of equations have a derivative of -2x. All of those curves are -x² plus a constant. So if you graph -x squared plus a constant, you get big negative slope, big positive slopes, 0 slopes, negative slopes, big negative slopes. So all of these solution curves all look the same way. They're all vertical shifts of each other, hence the plus C, and they all have that feel of big positive slope toward a 0 slope and then toward a big negative slope. If I may show a second one, what about dy dx is 1 minus y? 1 minus y. It's less clear what the solutions are here. And let's see, let's make the dots a little close together. That's just changing the scale so that I can go all the way up to 3 on the y-axis. And maybe we'll only go down to -1 on the y-axis. Let's just take a look at this part of the coordinate plane. Every time the slope of the tangent line is 1 minus y. So for every place where the y value is 3, the slope of the tangent lines we'll draw is 1 minus 3. That's -2. That's -2, -2, -2, -2, -2. And then the slopes of the tangents when y is 2. When y is 2, the slope of the tangent is 1 minus 2. That's negative 1, negative 1, negative 1, negative 1, negative 1. And then through here, the slope of the tangent line is 0. 1 minus 1 is 0. And then here, the slope of the tangent lines are all 1. And then here, the slopes of the tangent lines are all 1 minus negative 1. That's positive 2. And so this sort of helps us to see what the slopes of what the solution curves would have to look like. As we sweep from left to right, they come from big negative slopes down to what appears to be a horizontal asymptote here. It appears that the curves look like this, or if we're going through this point, they appear to look like that. So slope fields or direction fields are great for us to get a sense of what the curves look like. They give us a visual that help us see what solution curves look like. By the way, all of the solution curves to this differential equation are some constant times e to the negative x plus 1. That's just bonus. Something you may want to try: what happens if dy dx is x minus y? And let's look at that on -2 to 2 and -2 to 2. Let's look at it on these 25 dots. So pause the video, make yourself a slope field, and in a moment, I will magically display the answer. Are you ready? I'm going to magically display the answer in a moment. Looks something like that. And that's just weird. So we ask ourselves, what might the curve look like that passes through the origin? What might a solution curve look like that passes through the origin? Well, we know as we sweep from left to right, the slopes get smaller. So we know that it would sweep something like this. And then it looks like this line is a slant asymptote. And so we'd approach like so. And this helps us see what the solution curves look like. It looks like the solution curves look like this. But coming from the other side, it looks like the solution curves just come straight. I hope that this is helpful. The next screencast will look at Euler's method, and that's a numerical way to look at differential equations.